equals f prime times dx. So we have a differential dx and we have a differential dy. Now you recall that dy dx is another notation for the derivative f prime of x, right? The dy dx is called the Leibniz notation. Well, if you just think of multiplying each side by dx, then you can see where this idea comes from. So it says up above here, dx is an independent variable. It can be given any value, but once it is, then the differential dy is dependent on what the dx is. Now we have a picture here to help us understand this graphically or geometrically. And I'm going to do some writing on this picture and then erase it because otherwise it'll be much too crowded in the end. But first of all, we want to look at this delta y value here. This is the actual change in function output. So f of x is changing by some amount delta y. So notice that in this picture, so we have a x value here, and then we move a distance to the right, a distance of delta x, and we're at the point x plus delta x. So you notice, and again I'm going to be erasing these things in a minute so it doesn't get too crowded, but it tells us that the differential dx is equivalent to whatever delta x. So those are two notations for the same thing, that is how much we move from our initial point of tangency at x along the horizontal. Now this delta y, so we have a point P. Its x coordinate is x, its y coordinate is f of x, and then we have a point Q whose x coordinate is x plus delta x, and whose y coordinate, because it's on the blue function f of x, is f of x plus delta x. So when we subtract those two, we get this blue delta y. All that is how much the output changed when the input went from x to x plus delta x. So it's designated in blue to go with the blue curve, which is f of x, right? And so if we increase our x by an amount delta x, which we can also call dx, then our y will change by delta y on the function f. Okay, let me erase that and go to the next part. Okay, then we have this dy, right? So we have a point, let me call the tangent line L of x. We have the point P and we have the point R. And you see this dy is the amount that the tangent line's output is changing, right? So dy is the actual change in the tangent line output again when the x changes by delta x or dx. And what we're saying is we can use this to estimate the actual change in the function delta y. So dy, the differential, is how much change there was in the output of the tangent line. Delta y is how much change there was in the function itself. And we can use that dy to estimate the delta y. Now, in fact, we don't usually estimate strictly, well, okay, let me back up. So remember from up above, dy is f prime of x times dx. So basically what we're saying is we're prorating, right? So note that derivative, f prime of x, is being prorated hope you know what prorated means. I'll talk you through an example. I don't know that I have space to write it here. So remember, we can think of that derivative value f prime of x. We can think of that as the approximate change in f. We did this back in chapter 2. The approximate change in f when x increases by 1. Let me just erase this over here as well. So when we take f prime and multiply it by dx, we're actually prorating how much we expect the y to change. So for example, if f prime was equal to 4, then part of what that means, that's the slope of the tangent line is 4, the instantaneous rate of change is 4. There's many ways to think of it, but one way is if the x were to increase by 1, then we would expect the f to increase by about 4. Now, what if the x doesn't increase by 1, it only increases by half? Well, then we expect that y to only increase by half of 4, only 2. So multiplying by dx, that would be the half. What if x doesn't go up by 1? What if it only changes by a half? Well, dx is the amount of change in the x. So when we take the slope f prime, that is how much change we expect in y for x increasing by 1, and then we prorate that and say, okay, but x is not necessarily increasing by 1, it's increasing by dx. Multiplying those two together tells us how much we expect the y to increase, or change, because it might be a decrease if the f prime were negative. So they're talking here about directed distance, right? Again, that differential dy is f prime times dx. So dy, as it says here, represents the amount that the tangent line rises or falls, whereas delta y represents the amount that the actual function rises or falls. And it says, notice from figure 6 that the approximation becomes better as delta x becomes smaller. So again, I'm going to write on this and then I'm going to erase what I did. So we have this much difference between how much the tangent line went up and how much the function went up. If we move back closer to the point of tangency and compare here, there's not as much difference between how much the tangent line went up and how much the function went up. And if we pull back even further, we can hardly tell the difference at all between how much the tangent line increased versus how much the function increased. And that distance between the pink tangent line and the blue curve is the difference between the dy and the delta y. So basically what we're saying is that as the delta x, or dx, goes to 0, in other words, we move closer and closer to the point of tangency, then that dy, differential change in the tangent line y value, is getting closer to delta y, the actual change in the function.